All right, so let's get started.
All right, thank you. So what I'm going to talk about today is some peer-to-peer traffic localization without tracker support. So I hope you are a little bit familiar with how BitTorrent works. So you should know what a tracker is. A tracker is simple, very simple server that a peer would connect to in order to retrieve a list of peers where you can download some content. So ideally, when you want to get some content in BitTorrent, you go on any website, you're going to try to find what is called a torrent, and this torrent is going to contain address of trackers. Then you connect to the trackers, and the tracker is simply going to tell you, if you want to fetch this content, this is a set of peers you might want to try to talk to. So what we want to do is localize peer-to-peer traffic or maintain peer-to-peer traffic within an ISP without using the tracker. So try to use something else. First of all, I'm going to try to motivate. Well, let me first introduce which kind of traffic we're talking about and what is peer-to-peer traffic localization. So here we have a very simple representation of the internet. We have different ISPs with some peer-to-peer clients and a transit ISP. So when you try to get some content in a peer-to-peer network, this is what might actually happen. You want to download some content, you go to a tracker, the tracker gives you some random IPs that previously announced that they have this content. The tracker doesn't really know where these IPs are located, doesn't really care. It's just going to tell you, hey, try to download from these IPs. So most of the time, because your ISP is small and the word is big, you're going to go through a transit link and fetch the content from some external peers. What you actually would like to do is something more like this, where if possible, you try to get the content from a peer which is close to you. Close means same ISP or whatever metric you want to try to consider. In our case, we're assuming we want to have a peer located in the same ISP. So in this way, we're able to save the transit traffic, which is very expensive for the hosting ISP. So this is a well-known problem. Oh, I might need to get some power. So this is a well-known problem in the peer-to-peer community, and in the past, it was solved by using the tracker. So you can think about it in a very simple way. You go to the tracker, and the tracker gives you a list of peers, and if the tracker is informed about the location of this list of peers, it can actually try to give you peers, thank you, which are located in the same ISP. So if you have a tracker, if you can control the tracker, it's a very simple problem. You simply have some sort of eye tracker, as it was proposed in the past, talking about like P4Peer or a solution like this, thank you, that allows you to control the tracker and give you kind of information. So it becomes very easy to achieve peer-to-peer localization. But what if you want to do peer-to-peer localization without the tracker? So this is what we're trying to talk about. We're trying to solve, and this is going to be like what I'm going to talk about today. So first of all, I'm going to motivate a little bit better why we need to do this without using a tracker. Then I'm going to talk about our solution, which is called DHT traffic localization. Hopefully everybody knows what a DHT, distributed hash table, is. I'm going to throw a working example. Then I'm going to present some measurements we've been performing on the biggest BitTorrent network, which is called Mainline, about 15 million users. And then I'm going to conclude my talk. So,
hello.
First of all, do we really need peer-to-peer traffic localization? When we started this project a few years ago, people were like, you don't need peer-to-peer traffic localization because anyway, peer-to-peer traffic is naturally localized. I'm in the US, I'm interested in some English-based movie. Most likely I'm going to find them in the US as well. I'm not going to get them from Italy or from France. So there is some sort of natural localization in the content. So we run a very simple experiment, which is trying to download some of the most popular torrent and see how much traffic is in fact localized. If I just try go on BitTorrent, download the 100 most popular torrent as indicated by the Pirate Bay on, this was January 2012, I download them, how much traffic I'm going to get from some local peers. And what you see here is that it's really a few. In the best cases, which is for some of the most popular content, the highly ranked one, only 20% of my traffic would come from the same ISP. The rest of the traffic would come from all over the world. So it seems there is actually a problem. Now, do we really need the DHT? Do we really need to do something else in the tracker? You know, in the past, people have proposed to inform the tracker about the network coordinates of the user, so that the tracker can tell you where to download the content in a localized way. Do we really need that? Do we need an alternative to these trackers? You know, simply use the tracker solution is going to work fine. So this is just a summary of what has been happening in the last years. Many of the trackers are being shut down because of some copyright infringement. So police is just knocking at the door and shutting down their servers. But what is not shown here is the latest thing that actually happened is the Pirate Bay stopped serving torrent. So you cannot go on the Pirate Bay and get the torrent anymore. You can go on the Pirate Bay and get something which is called a magnet link, which is a different thing, which is not going to contain any more address of trackers, but it's just going to contain an info hash of the file. So this info hash of the file is some coordinates you can use in a distributed hash table to get the content you want. So BitTorrent has introduced the concept of the distributed hash table, which is just like a distributed tracker that you can use to identify the peers that hold the file. So in the classic BitTorrent, you go to a server, you get a list of peers. Using a DHT, you go to DHT and you get this list of peers. But going to the DHT means that you're not going to a given tracker, you're just going to another peer in the peer-to-peer network. So the peer-to-peer network now is completely self-sufficient, there is not any server anymore. So it's easy to say that without the server, without these trackers, any tracker-based localization is not going to work anymore. You need to do something in the DHT if you want to be able to localize peer-to-peer traffic. So since this wasn't enough, we ran some experiment in a customer ISP. So what we did is that we just installed some rules at the edge router so that we can, every time there is a packet going to a tracker, we kind of keep some statistics. So we're trying to understand how many users from this ISP were going on BitTorrent and they were using a tracker. And at the same time, we build a tool to monitor the DHT. And then we filter, we adapt the tool to work for this specific ISP. So now we have a view of the trackers and we have a view of the DHT. So what we see here is a very simple snapshot of the number of users over time divided by the one that are just using the tracker, the blue line, the one that are just using the DHT, the red line, and the one that are using both, the orange line. So the key message here is that if you're just running a tracker-based localization mechanism, you can only capture like a third of your user. If you want to be able to capture all the user, you need a solution which is both using the trackers and the DHT. Because if your solution is just using the trackers, for every user here on here, there is nothing you can really do. If the user is just using the DHT, it's going to look for some content, you don't even see the request, and BitTorrent is going to behave in the same way. If you are on the orange curve, you're localizing the trackers, so a fraction of the user you can return is going to be localized, but the other fraction is not going to be localized. So of course, this is going to detract from your performance. So hopefully I convinced you that we need something else, that tracker-based localization is not enough, and that we need to build a distributed mechanism to localize BitTorrent traffic. And this is what I'm going to talk to you right now, and is what we call DHT-based localization. So in the same way as you can inform a tracker about the location of the user, you want to inform the DHT about the peer's location, so that the DHT can actually make some informed decision. The problem with the DHT is that there is no owner of the DHT. It's a completely distributed system. It's not like you can propose a modification of the protocol or stuff like that. You need to play with the DHT in a way to achieve that goal. So how can you control a DHT? So there is a popular attack, which is called the Sybil attack, which allow you to control a DHT. So usually we represent the DHT as a ring because it's a hash space and it's so it's easy to represent as a ring. Let's say this is a DHT built across the internet where you have like a 6 user and 1, 2, and 6. And then you have Sybils. What is a Sybil? A Sybil is a peer in a DHT, in a peer-to-peer network, in this case in a DHT-based peer-to-peer network, which it's a physical peer, but he has multiple identities. So basically I'm going to choose the hash of these peers very close one to each other, and I'm going to store them in my DHT. So when you participate to a DHT network, you get an ID, and this is just a hash, it's a random value. In this case, I'm going to force my logical identities to have many IDs that are very close to each other. So what's going to happen is that I completely control this part of the DHT. So every time there is a request, I'm going to see this request. So for example, if somebody is going to publish something which is going to fall in that range, I'm going to see that request. Same thing, if somebody is going to looking up for that information, I'm going to see this request. So this Sybil attack was proposed in the past to control a DHT. So to make sure that if I want to hijack some content, I can. The way we twisted this attack is in a positive way, extending with the peer location. So we just insert Sybils in the DHT, and these Sybils, every time they see a request from a user, they also localize the user, so they know where the user is located. And we do that by simply using MaxMind database. So now, when I see a publish for some content, I also know that this publish is coming from a peer located at Comcast, for example. And I'm going to store the information in a local database. So that every time that I see a request, in this case from a peer looking for the same content and located in the same ISP, I'm just going to map this request to that peers. So what a regular peer will do in the DHT is to just pick randomly from its local database. What we're doing here, by doing something like this, is that we are going to select the peers, we're going to match the peers based on their location, because our final goal is to maintain the peer-to-peer traffic local. So once you've done that, then the file transfer can start, and of course it's going to be a local file transfer. So which file should we localize? Ideally, you want to localize all the possible files in a peer-to-peer networks, which is millions. Because I told you you need Sybils to insert in your DHT, you're going to need Sybils, multiple Sybils per each file. So that means that your resource is going to scale linearly with the number of files, so it is impossible to do. But at the same time, localizing the traffic for each file is not necessary. In order to have traffic localization, you need to make sure that there are at least two peers located in the same ISP. So if you're thinking about a very unpopular file, maybe you have 10 copies all around the world, the probability that that file is going to be available in your ISP is very low. So because this solution is an actual product that we developed, people were coming to us and they were trying to get motivation on how many of these files should we localize. We had we were buying server resources to run the Sybil, and we need to know how much money we should put in there. So how many of these files should we localize? So we had 4 ISP that went through a trial, and they wanted to know, okay, what is our localization potential? So if you could localize all the files, how much? I'm not asking you to do that. Just tell me how much can you localize per file. And this is the result. If you look at, this is just the fraction of torrents we were looking at, and this is the localization potential, which is just at a given time, if I'm trying to get some content, how many local peers I can find versus the one outside. So this is actually telling us that only 1% of the file actually has some localization potential, which means there is some traffic we can save. The good thing is that this 1% is accounting for more than 60% of the overall traffic. So overall, you're actually going to be able to make an impact on your ISP.
So, quick question. So, what exactly is involved when you say we have to monitor a given file?
Yeah, so
generate Sybils for that file.
So the way you build the Sybil is very simple. You decide your own ID, and then you join the peer-to-peer network, which means you start talking with your neighbors, peers in the DHT. There is a routing protocol, of course. We're going to run these routing protocols. You send ping and hack and stuff like that. So basically, there is traffic you have to generate. And we also make our Sybils very chatty, so that everybody knows about us. We kind of want to enforce that we are there, and everybody's going to try to talk to us. So Of course, you don't need one Sibyl profile because requests are going to come everywhere from the DHT. You kind of want to cover a region. So the number of Sibyls might be like 1,000 of Sibyls you want to have for one specific file. So at the end of the day, it's Sibyls equals to, think about a EC2 machine that you need to pay, and memory, and hard disk space, and CPU that you're going to have to pay. We actually did a study, I'm not going to talk about it, but we actually did exactly this. We were, we were trying to understand if we could be profitable or not, and the way we did it was really trying to understand we can localize this amount of traffic, and it's going to cost to us this amount. Of course, the best thing for us is localizing one torrent for multiple ISP. If I go to an ISP and say, hey, if you give me $10,000 per month, I'm going to localize you 100 torrents, and then I can come to another ISP and say, hey, I can localize the same torrent for you too. I'm not going to need more resources for that, but I'm going to make more income. So you actually can find the breaking point based on the number of customers you have to have and stuff like this. So how does it work? So we build the system. It's something we actually had running for like 6 months. We had few customers, and once we run the system, so that means we have some popular torrent we are localizing. What you see as a user, let's say it's your ISP, you go on Pirate Bay and you pick one of the popular files. Let's say you are in Comcast, you start uTorrent, and you start downloading, and ideally you only see peers from Comcast. And once you're done downloading, what you're going to do is that you're going to announce to the DHT, hey, I'm done. I actually have a copy. So this is what we consider the proof that our solution works. You're going to send these messages, which are called announce message. You can read here announce, which only say, okay, I have a full copy of this content, I can actually serve it. And if you announce that information to my Sibyls, that means nobody else in the DHT knows about it. I only knows about that. So nobody else can come and get that content from you because the DHT doesn't really know. I'm the only one that knows. So I'm kind of like re-centralizing the DHT. And this is showing you with what actually happened in this experiment. So because we built this, we had, it's kind of interesting, like you can build this solution, you can run it, and nothing happens, which means I'm localizing traffic, but if I have no control on the end user, I would never know how much traffic the end user is getting. The solution we were talking so far is just a server-based solution. I can see how many requests are coming, I can measure all that, but I have no idea how much traffic you're getting localized. So we have to build also a client-based solution, which is more like a measurement tool. Our goal was to measure the localization benefits, or the fraction of traffic that would stay local based on the clients you're using. BitTorrent has several implementations, uTorrent, transmission, BitCommon, to name a few. We wanted to know whether the client you use has an impact, the ISP you're sitting at might also have an impact, and the torrent, if you're downloading a very popular one or an unpopular one, for instance. So we have implemented a bunch of tools that allow us to play with all this. The first tool is very simple. It's just looking at pickup traces to extract the period you're downloading from, their location, and kind of derive the fraction of traffic which stays local. And we have been running this with uTorrent, transmission, and BitCommon, which are the 3 most popular clients. And you'll see later what we found. For the ISPs, we could play with these 5 ISP, Free in France, Comcast and Verizon in the US, Telecom Italia in Italy, and Belgacom in Belgium. And basically this only means we had access to machine there. We first used PlanetLab to run some experiment, but it was very unreliable. We couldn't really tell what was happening. So the best solution was, the good thing was we had access to many ISPs, but it was very hard to really get an understanding of what was happening. What we wanted to know was, oh, we see this localization and this is the reason. Because when a customer would come to us, by just analyzing the customer ISP and what they could tell us, we wanted to try to predict if our solution was working good or not. And PlanetLab was completely unreliable for that level. By having control on reliable machine, we kind of were able to shed some light on that. In order to run an experiment in there, we didn't use the pickup-based tool. We actually modify a BitTorrent client to log information about the peers and their location and stuff like that, just because it was more convenient to run, since like uTorrent run on Windows and BitCommon too. And then about the torrents, we want to try to understand how we work based on the popularity of the torrent. You could perform very well with a popular torrent, but with an unpopular one, you would perform very poorly. This is what kind of makes sense. So this is what is really hard, is to tell which torrent is popular in a given ISP. Today you can go on the Pirate Bay and click on the top 100, the most popular one, and this is telling you the 100 torrents that are the most popular. But this is not telling you which one of these torrents is popular in Telecom Italia. So if you go on the Pirate Bay and you fetch the top 100, and then what we did is that we start localizing traffic for this torrent, which means we see all the requests coming. What we're plotting here is a CDF of the average number of sources for this file. Number of sources means, remember before I told you, when you're done downloading a file, you send these announce messages and we capture them. So whenever we see that, this is a source. And of course, this is going down over time, because in the DHT, you need to maintain those copies. So you need to keep saying, hey, I still have a copy, I'm still here. So because of the churn, this is a CDF. And you can see there is a big difference between Belgacom, which is the one where the most popular torrent only has like 20, 30 sources, and for instance, Comcast, where we go up to like 200, 300 sources. So the popularity, those are the same files. They're just differently popular in the different ISP. The ISP has different size, and at the same time, they are located in different regions. So what is popular in Telecom Italia is definitely not popular in the US. So this is a per se problem. I mean, looking at the DHT and try to estimate torrent popularity, either info edge popularity and distribution over time and region, it's a new problem, and we have no solution for that. What we did was doing something like this, which approximate a little bit the real problem. So the first thing I want to show you is what I call the responsiveness. So first question we received from a customer is, okay, so you want to localize my traffic, but what I see is that these peer-to-peer files are very, I see flash crowds, and all of a sudden I see a lot of traffic for one file. How fast are you? How fast can you react to something like this? Some of the ISP were willing to tell us, oh, we want to localize this specific torrent, but they want to know how fast can we actually do that. So this is a very simple experiment where we show between start and stop. We're starting the localization, we're stopping the localization, and we're going to see what is happening in the network. So on the x-axis we have time, is a 30 hours experiment, and on the y-axis the number of sources. So number of sources is the number of sources for a given file. So at the beginning, our civils are not there. So if you try to download these files, you're all getting non-civil sources. So the civils don't know anything about these files. We don't know anything about the file. Then all of a sudden we started, and in about 15 minutes, this is the time required to the DHT to learn about our civils, spread the information enough so that all the announces now are coming to us. And so what you're going to see is that the non-civils start not to receive, they still receive a large fraction of announces, and this is something that we weren't expecting. They still receive some announcement, but way less than before. And our civils see about 100, 150 announces. And for all the time that the civils are running, we see the same thing. Then we stop them, and again in 15 minutes, the non-civils take over, and we completely disappear from the system. So 15 minutes is kind of like the response time, both in installing the system, starting the localization for a single torrent in the network, and then stopping it for the same torrent. Why 15 minutes? Simply because this is like a timeout that you have in the DHT network where you should re-announce. So 15 minutes is enough for us to spread all the information about our peers, and then when everybody else will start re-announcing, in the worst case, you'll have to wait about 15 minutes to learn about everybody else.
How do you measure what non-civils are seeing?
So
you have no control over the non-civils, right? So how do you measure how many requests they are seeing?
No, that's a good question. So we do it in a passive way. So I start downloading that torrent, and I see how many sources I'm receiving. Okay, so the DHT is there. Somebody knows about a given torrent. I start the client, and I start downloading, and I start receiving peer list. And that's what I'm plotting here, is the number of sources for that file that I see. And then I start the localization somewhere else, from Amazon. And then from the same client, I keep doing the same thing, and I will start seeing that the sources from the non-civils go down, and the sources from the civil goes up. So we do it from a third point of view.
So essentially, it's measured on the client, right?
Yes, on the end user.
So one question is, you obviously can't control how the clients remember or forget sources,
yeah,
right? So it's possible that they remember sources before your civils take over.
Yes, but in this experiment, our cache was empty, so this wasn't happening.
Okay. The other thing is, never mind. So I'll ask that.
But now I'm going to explain you why we still see non-civil sources. If you're trying to understand why there are some non-civil sources, I'm going to talk about it right now.
Okay.
So, ideally, we control the DHT, we see all the requests, nobody else should see the request, why there are some non-civil sources. So, this experiment here is a very simple one-day experiment where we download the most popular torrent at Comcast over 1 day for every hour we download it once, but using 3 clients. We're using uTorrent, we're using transmission, and BitComet. And y-axis is the fraction of traffic that stays local, and x-axis is the time. So uTorrent transmission, yeah, there is some variance, but it's working pretty well. More than 90% of the traffic is local. BitComet, there's not much we can say. I mean, sometimes it's bad, sometimes it's good. We don't know what's happening. So we now introduce a very simple metric, which is just the ratio between the non-civil sources and the civil sources. So what we saw before divided in the plot before, now we're just plotting the ratio. So what you see here is that for uTorrent and transmission, very similar behavior. Most of the time is more than 1, so you have more civil sources than non-civil sources. But for BitComet, it's exactly the opposite. Most of the time, you're getting more sources from other peers than from us. So that means that we're not really capturing all the announced messages. And why is this happening? Well, if you look at BitComet, what BitComet is doing is that BitComet clients are not announcing to us. So they are supposed to implement the DHT protocol in a given way, and they don't. They build a private network across BitComet clients that they tend to favor. So first of all, they will try to stop connection to uTorrent and transmission client. If they can't talk to BitComet, they will talk to BitComet. And the announced messages is going to be first on the BitComet clients, independently of the hash space, then on us in some cases. So this is the reason why the localization is not working fine for BitComet clients, and is also the reason why uTorrent and transmission see some non-civil sources, because we cannot control the BitComet client. They're doing something else, and then of course, when I try to download, I might eventually get some sources from other peers that are not supposed to know that. And those are only the 3 most popular clients. If you look at other clients, we actually play with KTorrent and other RTorrent. Because they don't implement the DHT protocol perfectly, they might miss some announced to our series. So of course, this is detracting from our performance. The good thing is that uTorrent and transmission cover like 80% of the clients worldwide. So at least we work in the best way for the most popular clients. But there are some countries in South America where BitComet is the most popular one. There is no reason to try to use our solution there, because it just doesn't work. So the second experiment is now trying to understand the impact of torrent popularity on the localization benefits, so on the fraction of traffic that stays local. So we pick 4 torrents, the most popular, so we're talking about Comcast, single ISP again. We have the most popular torrent in Comcast, and then with 75 percentile, 50 percentile, 25 percentile. So we go from the most popular one to least popular. And popular means highest average number of sources over a given time period that we monitor. And then what we're doing is that for these 4 torrents, we download them at the same time every day for a month. And then we, we're just plotting a CDF of the local download traffic, so the amount of traffic that stays local. As we said before, the traffic is not always local, it's not always 100%, because there are some events we cannot control. But on top of that, we can see that as the torrent popularity goes down, the fraction of traffic that stays local is reducing. So the torrent popularity is also playing an impact. But for the last torrent, torrent 4, we kind of see that, yes, to some extent this is still true here, but then in some cases we actually get very good performance. So this torrent is very unpopular, but in some cases we get better performance, and performance means fraction of traffic which stays local, even better than the second most popular one that we have. If you just look at this plot, you have no idea why, so we need to dig a little bit deeper. So we introduce a very simple metric, which is the non-local to local ratio. It's the same thing as the non-Siebel divided by Siebel, but a little bit more generic, in the sense that in some cases you're lucky and your non-Siebel sources are actually giving you local peers. So this is actually capturing something a little bit more general, and is telling us how many non-local versus local peers we receive from whatever sources, Siebel or non-Siebel. So then, if we now look at the scatter plot of the local download traffic and the metric we said before, rho, it should be very intuitive that we see this sort of behavior, right? So let me see if I have an animation or not. No. So if you are here, your local download traffic is very high and rho is very low, right? So this is very intuitive. I mean, I'm mostly connecting to local sources and I get a very high download traffic, local download traffic. This makes perfectly sense. And this makes perfectly sense as well because I'm connecting to mostly non-local sources and my traffic is unlocal. But at the same time, we would see something like this. We see that the local download traffic is very high, but I'm connecting to many unlocal sources. In this case, more than twice unlocal sources than local. So it means that I'm talking to 40 peers all over the world and only maybe 20 inside my ISP. But still, I'm getting 95% of my traffic, which is local. So why is that? It's of course because of the speed. If I'm talking to a bunch of local clients that are very fast, they might be able to give me all the content I need in a very short time. So the external sources, which might be slower, they don't have enough time to give me content and so reduce my amount of local download traffic. So I want you to focus on the high curve here, which is the magenta one. What you see here is that the local download speed is about 10 times faster than the unlocal download speed. This is just a distribution per client. So this is exactly what I just said. It's very important, the torrent popularity, because of course the more popular you are, the higher the chance to have more peers in your ISP, and so you can fight better against the non-Siebel, which are trying to kind of detract from your performance. But at the same time, the ISP where you're running is very important. Comcast is a very fast ISP. So because of that, even when you're connected to only few clients internally, they might be so fast they can actually kill all the others. So this is actually working good for us if we have to work with fast ISPs. So the next logical step is try to understand what would happen in different ISPs. So what we see here, or actually we don't see much, so that's why later I will break it down. But it's just a summary of the experiment. So this is a week experiment. We have 5 ISP, Comcast, Verizon, Free, Telecom Italia, and Belgacom. And we are downloading the most popular torrent per ISP. So different torrents, not the same one. Because as I said before, it's impossible to find a torrent which is as popular in every ISP. They're all different. So we went for the most popular one, trying to hide the popularity, the torrent popularity problem to some extent. We download it every day from every ISP at the same time. So let's first focus on Belgacom. So Belgacom, it's all over the place. I mean, sometimes it's bad, sometimes it's good, mostly bad. This is the popularity effect. So if you look at the picture I showed you before, as I said before, we're downloading the most popular torrent. This only has about like 20 or 30 sources. Okay, so if you compare with Comcast, this would be what, like 40% time, right? So this is a very unpopular torrent in Comcast. So now if we go back to what we saw before, torrent 4, you can see that it's kind of all over the place. So the behavior we see there, it's very well representative of an unpopular torrent. So we're just, because the popularity, this torrent is very popular in Belgacom, but overall is not a popular torrent. What you can see is that this is just a popularity effect. This torrent is just not popular enough to guarantee our localization mechanism to work. Now, what about Telecom Italia? Telecom Italia is working perfectly. You know, it's 100% all the time. Then one day we went down to 80%. This is what we call the ISP effect. So if we now look at the scatter plot of the local download traffic and this ratio, the raw ratio, and again, it's the number of local sources, non-local sources versus local sources. This makes perfectly sense. 100%, but the ratio is extremely low. You see, it's way lower than everybody else. So the ISP is doing something. Somehow the ISP is blocking the connection with external sources. You know, we have been discussing that before. Somehow the ISP is trying to make sure that your client is not talking outside. But for this point, where, again, this point makes sense, you see we go down to 80%, and the fraction of traffic, the fraction of non-local sources gets higher. More in the range of the other. So this is like a normal behavior. The other behavior, we believe the ISP is doing something. It's somehow blocking the connection to external client, which is indeed helping us. All right, so to summarize, I hope you are convinced that we need DHT-based localization. If you want to maintain peer-to-peer traffic, you need to control the tracker, but at the same time you need to control the DHT. If you don't control the DHT, a huge fraction of peers is going to detract from your performance. And we saw that controlling the DHT is hard. Because the DHT is a big environment with different implementation, there is no standard, you can implement the protocol as you want. It's way harder to achieve localization than with a tracker. You know, with a tracker, it's a server you write, so you can actually implement perfect localization. The one thing which is missing here is another mechanism that BitTorrent is implementing, which is called the peer exchange protocol. This is a third mechanism for finding peers, and basically it's like gossiping. So if I know some peers and I happen to meet you, I might tell you, hey, if you need this file, you can download from these peers. So of course, this third mechanism, impossible to control. The only way to control it is controlling the client, telling the client to only inform other peers based on locality information, which is, you know, is a solution which is not going to fly because it requires, we have like a 20 BitTorrent implementation, everybody would have to implement that, and it's never going to happen. Maybe you convince uTorrent to do that, that covers 50% of the clients would be, you know, already pretty big. But usually everything that concerns change the client in peer-to-peer network doesn't usually work. You want like a transparent solution. And of course we cannot capture that. But if you achieve very high localization, then the gossiping is going to actually help you because you're just going to spread the information which is already good information. It's not going to be bad information. So we built the solution. As I was saying before, this was a startup we had like 4 years ago. We built it, we run it, we have customers, we make some money. And the good thing is that we could make some nice measurements. The key results we saw is that it works pretty well, but for Bitcomet. For Bitcomet, forget about it. If your ISP has a lot of Bitcomet clients, don't use it. we were trying to understand a little bit better how it works, I mean, what plays a role, and definitely the download speed that each single peer can provide is important. So if your customer is a fast ISP, it's going to work really well. If it's a slow ISP, maybe a small ISP like Belgacom, where popular torrents are in fact unpopular, there they cannot be your customer. And the last thing that I didn't show, but it's a nice story. We were working with a Korean ISP, and this Korean ISP, their goal was to reduce the transit traffic. I mean, they don't care how you reduce the traffic, they just want to save money. So they came to us, we implemented the solution. We were measuring like 40% of their BitTorrent traffic going down, but they were just measuring their transit traffic and it was staying constant. Well, it turns out that as soon as we removed some BitTorrent traffic, HTTP traffic was coming and was getting that bandwidth. So their user might get a better user experience, but they were not saving money and they were not happy. But of course, we cannot do. I mean, there's nothing we can do. All right, thanks.
All right, questions. Let's let the speaker first.